morning, everyone. Thank you for giving me an opportunity to present my work, which was performed by one of my PhD student on standard gravity and wind load analysis on 103-year-old unreinforced masonry building. The work was initiated on one of the structure, which is excellent example of Indo-Saracenic style architecture, which was introduced by British during their rule to colonize India. The outline of my presentation are as follows. I'm going to introduce about our work, then about Senate Hall, in situ survey, then model prepared in FEM tool, ANSYS workbench, its analysis and results, and further conclusion will be shown to you. So Allahabad city is one of the oldest holy city of India, also known as Prayagraj, and associated with the mythological personality in Vedic and Buddhist literature. Sage Bharadwaj, which you can see on the right hand side of this particular slide in figure 1, lived in circa 5000 BC and taught more than 10,000 discipline. He was great philosopher of ancient world. The city was fairly a long span of time for the Mughals, including colonial down to contemporary, with there are various structure which were built by Mughals, that is Allahabad Fort, Khusro Bagh, Ulta Qila, and then Britishers came in. They started building Allahabad High Court, Allahabad Public Library, Allahabad University, All Saint Cathedral, etc. So if you see this, this is a finite element model of Senate Hall, and this is a very nice example of Indo-Saracenic style architecture. It was established in year 1887 and was designed by Sir Swenton Jacob in 1910, and the construction was carried by Lieutenant Governor Sir John Havett in 1915. So this was an effort by Britishers to integrate a British and Indian ambition in the year 1858, soon after the first Indian you can say revolt, which was. So further you can see various cracks, etc. During the survey we observed minor cracks in these structures. This is another slide which shows various part where the cracks has been seen. So again the next slide shows figure 7, 8, 9, 10, shows the deterioration, etc. in the building, and the minor cracks of approximately 1 mm to 5 mm are visible on the masonry wall, stone facade, crown of the arches, and connections of the ground floor. And the major cracks approximately you can say 5 mm to 20 mm are. Further, if you see, the ground floor plan has been prepared using map and the drawings which were provided by the authorities, and the overall length of this particular Senate Hall building is around 130 meter, and the width is approximately 38 meter. So it's quite a big building which is having 3 floors, and if you see the internal hall is quite big. It is approximately around 40 meter by 18.3 meter in the width. So this hall is purposely used for various cultural and other programs in the Senate Hall building. So this is quite important building for administrative work for Allahabad University. So here I am showing you the basement plan of this building. So I can why the purpose of showing this is to show that entire building is quite symmetrical, but only this portion, the back portion of this building, which is on the south side of the building, is having a basement, and the basement is of around 31 meter in length and approximately 11.43 meter in width. And the width of this width of the wall at the basement level is quite huge. It is approximately 1.5 meter. So this definitely used as a storage purpose, and this is a entry from where they enter the basement level. So this is again, I want to show you that there are various towers in this building. So this is a central tower which is also used as a circulation purpose, and it consists of a clock, and it is the highest tower, which is approximately 30 meter in height. Further, we have two towers in the front, which is also known as side towers of the building. Again, it is used for the circulation purpose. You can see the stairs are there, and it is approximately 26 to 27 meter in high. We have another set of towers on these buildings. These are lower than the tower which is there on this side, and we have a back tower as well. So the back tower is of boat shape. I will show you in the FEM drawing, and all other are having a dome, and those are all supported by stone columns. So again, this is another tower. So this comprises approximately 11 towers, including this central tower. So if you see this, we used macro and homogenization technique to prepare this FEM model, and this model has been prepared in ANSYS workbench, that is version 14, and I am going to show you that figure 13. We didn't consider any decorative material for this particular work, and also in the current work we haven't considered the cracks, etc. We just prepared a model based on the actual dimensions, and the mesh size were used after convergence criteria. So we have used 600 mm for the masonry wall. For the roof we have used 160 mm, for dome 120 mm, for arches it's 100 mm. So altogether it's approximately 1.2 million nodes were there, and approximately 470,000 solid elements are created for this model. So it's a huge model, and it's to prepare this model is around 3 to 4 months of time. So the element used for the solid and surface element in the model are solid 186 and 187 and surf 154. Further, the element while we join them is using targ 170 and conta 174 using bonded behavior. So these are the properties which you can refer to the ANSYS library, and you will see they are quite good, you can say, in order to predict various behavior of the structures. So we prepared a finite element model, and as it shows that it's quite symmetrical in the plan, except the back portion plan, which I've already discussed. They have a basement at the bottom, but all other part is quite symmetrical. If you see all 4 towers, those are quite symmetrical, and even the side towers are symmetrical. The boat shaped towers, inverted boat shaped towers, are also symmetrical. So this is quite symmetrical structure. I'm also showing you mesh model of this particular structure. So if you see, different color shows the various meshes which is used in this particular entire 3D structure. So this figure shows the cross section, and that too of mesh model. If you see this, these are the meshes, and I've already described all these mesh size what we have taken for each of these sections. And this is the back portion of the Senate Hall building, and you can see this is there, and I already mentioned that the wall thickness is of 1.5 meter. So this is quite symmetrical except this basement portion. So if you see this side as well as on this side, this is entirely symmetrical structure uh, on which we did the analysis. So very primary analysis, that is nothing but a gravity analysis, has been performed, and if you see this figure, um, the maximum stress which has been obtained is of 5.69, that too on the top of the clock tower. And this particular analysis is only conducted to see how the configuration of this particular structure behaves against the gravity loading. And further, if you see the cross-sectional part of this building, that is, we have cut around this direction, and if you see this, the maximum of 5.69 is obtained, that too at the basement level. If you see, this is around this corner, we have one basement which I have already shown in you in the plan. So we have obtained of around 5.7 megapascal of stress at this particular place. So if you see this particular gravity analysis, the total deformation of 7.80 is obtained at the top portion of the roof. Further, if we look into the global coordinate system, the directional deformation is maximum on the edge of the clock tower, which is around 1.44 mm, and in y direction it comes around very minor, it is 0.038, that too on the roof, and even again of 1.4 is in z direction, which is again at the roof level. Further wind load analysis were conducted, and if you see this particular portion of the tower, the maximum stress of 4.10 megapascal has been observed, and we observed a minimum stresses around this corner of this building. And if we see the cross section, even we found the maximum stress of 4.10 is also observed on the bottom of the side tower of this building. So for a wind load, the total deformation which has been observed is on the back side portion of the building, and if you can see this portion, the maximum of 8.0725 mm of deformation has been observed due to the wind load. I would like to conclude with the note that more rigorous analysis is required for such an excellent example of Indo-Saracenic style architecture, and this is one of the unique architecture which represents how British colonizes any country with their infrastructure facilities. Further, in situ investigation and retrofitting solution are suggested to conduct computationally expensive instrument, and time history method, kinematic analysis, and pushover analysis will give more you can say clear picture of present condition of this structure. Further, I also like to conclude that with this particular work we came up that the entrance ports of the building are more vulnerable on the ground floor level. I sincerely thanks to Engineer Naveen Kumar of Allahabad University who has unconditionally supported our work and provided all the assistance during our work to my PhD student. Thank you very much for your patience listening, and if you have any questions you can put it in the chat box. Thank you.